Welcome back again. So let's continue from where we stopped. We have already gone through the questions and just two of the questions. We will still do more as we go. So before I continue, I want to get into your head. I want to bring to your notice something. Take a look at this side of the board. When a hotter body comes in contact with the colder body, when a hotter body comes in contact with the colder body or a cold body, the hotter body loses heat to the colder body. When when a hotter substance or a hotter material comes in contact with a colder material, the hotter material loses heat to the colder material and it will continue to lose heat until both materials attain equilibrium temperature or equal temperature. Remember, quantity of heat, remember from our formula, from the formula for quantity of heat, remember we said that the amount of heat required to raise the temperature of a body is the heat capacity. And now the quantity of heat now is the amount of heat needed. Quantity of heat is the amount of heat needed to raise the temperature of a body. And we say that Q now is the amount of heat or quantity of heat always in joules, because this is the amount of heat energy needed to raise the temperature of a body. You know, temperature, the rise of temperature is as a result of addition of heat. That is why after solving some of our questions and then we get a negative answer, it means that heat was lost in that process, in that whole process, heat was lost. But when heat is gained, the answer would be positive. And we say that quantity of heat is equals to mass of that substance times the specific heat capacity of that substance times the change in temperature of that substance. Now we have known this, and we say that when a hotter body comes in contact with a colder body, the hotter body tends to lose heat to the colder body, and the heat transfer would continue until the both of them attain a stable equilibrium. Since we say this is true now, we can now say that quantity of heat of a hotter body is equals to quantity of heat of a colder body. You get? And from our formula, we say that Q is equals to MC change in theta. We can say that from this our equation here, we can take this one here or this one, whichever one, and put it here. So we say mass of the hotter body times the specific heat capacity of the hotter body times the change in temperature times the change in temperature of the hotter body is equals to the mass of the colder body times the specific heat capacity of the colder body times the change in temperature of the colder body. Now, before we continue here, we know that this is the change in temperature of the hotter body, and this is the change in temperature of the colder body. For us to get the difference in the change in temperature of the hotter body and change in temperature of the colder body, we can use this formula. We can say change in temperature of the hotter body is equals to temperature of the hotter body minus the equilibrium temperature. Because here we're considering three temperatures. We're considering the temperature of the hotter body, we're considering the temperature of the colder body, and now we are considering the equilibrium temperature. Because we say here that when the two bodies comes in contact, this one, let's say it's 100 degrees Celsius, and this one is 40 degrees Celsius, and when they meet together, that heat will be lost from the hotter body. So the transfer of heat, the hotter body now, the hotter body will transfer heat to the colder body until they stay in equilibrium, until the temperature becomes stable. And the stable temperature now is what we call the equilibrium temperature here. We can say that we can call it theta. So I can say where change in temperature of the hotter body, when change in theta H is equal to temperature of the hotter body, change in temperature. You can say this is change in temperature of the hotter body, of the hot body. And then theta is equal to the equilibrium temperature of the hotter equilibrium temperature. Equilibrium temperature. Let me just write it here for. And then C theta H is the temperature of the hotter body. Temperature of the hotter body. Change in temperature of the hotter body equals to temperature of the hotter body minus the equilibrium temperature. Because when these two bodies collide, the hotter one is giving out heat, and because it's giving out heat, the two bodies would attain equilibrium temperature. So after mixing hot water and cold water, that equilibrium temperature that you use to bathe or use to take your tea, that final temperature where the water has gotten and you use it to bathe or eat or drink tea is what we call the final temperature or the equilibrium temperature. So this is for the hot body. This is the change in temperature for the hot body. To get the change in temperature of the colder body, we say change in theta C, change in theta, that's change in temperature of the cold body, is equals to equilibrium temperature minus temperature of the colder body, where this is the change in temperature of colder body, of cold body, and this is the equilibrium temperature, equilibrium temperature, and this one is temperature of the colder body, of cold body. So you see, this for us to get a change in temperature of the colder body, we would say change in temperature of the colder body is equals to equilibrium temperature minus the temperature of the colder body. So now, since we have gotten this now, this is for the temperature of the hotter body, and this is temperature of the colder body. The change in temperature of the hotter body and the change in temperature of the colder body. Taking these two now, we can substitute them into this equation we have here. So we say mass of the hotter body times the specific heat capacity of the hotter body times we take this equation here for the hotter body. We are substituting this one. So we say times temperature of the hotter body minus equilibrium temperature is equals to, we do for the colder body. This is the cold body. This side is the colder body, cold. And this side is the hot body. So we now like take the change in temperature from, we take this part, we take this change in temperature of the hotter of the colder body and put in our equation. So mass of the colder body times the specific heat capacity of the colder body times equilibrium temperature minus temperature of the colder body. Now we use this equation now to solve. So this becomes our equation. So in general, we say MC MC of MH of the hotter body and C of the hotter body bracket temperature of the hotter body minus equilibrium temperature is equals to, sorry, MH, sorry, not MH, is equals to mass of the hotter body, mass of the colder body times the specific heat capacity of the colder body times temperature, equilibrium temperature minus temperature of the colder body. In summary, of all this now, heat gain, quantity of heat gain, quantity of heat loss is equals to quantity of heat gain. Please note this formula and note this formula. Also, I want you to note. I want you to note something. The mass here, can be the same. It can be the same. It can be the same with this one. It can be different. The substance here can be different. Let's say this might be mercury. This might be water. The both of them can be water even. So if the two masses are different objects or different material or different substance, it means that you have to be using their different specific heat capacity. Let's say you're mixing oil, you're mixing water and iron, you're pouring water and iron. We know that the specific heat capacity of iron is SHC of iron is around I think 460 joules per kilogram per Kelvin. And for water, specific heat capacity of water is 4,200 joules per kilogram per Kelvin. So if the two substances here are different, let's say this is water and another substance, maybe iron, or aluminium, or whatever, or oil, use their different specific heat capacity and so on then. But this one, it can be cold water and hot water. If it's cold water and hot water, it means that they are still using, you'll still be making use of the same specific heat capacity of water. This time around, you can cancel them out. If the masses are the same, you can do the same as well to help you solve faster. So that's for this now. Thank you. And we'll be solving more past questions as well in subsequent videos on this topic. Thank you very much.